So again, thank you very much for coming to the conference. I think it's very successful. I will talk about my work with Renan Barkana, which I started as PhD student, and I'm still working on investigating the effect of high redshift X-ray sources. I just recently moved to Harvard, but before that I was in Paris in École Normale Supérieure. So this is a cartoon of thermal history of the universe. At very high redshifts, gas temperature was coupled by collisions to and scattering to the temperature of the CMB. And roughly around redshift 200, the scattering became inefficient, and the gas temperature started to drop as 1 plus z to the second power because of the expansion of the universe, so just adiabatic cooling. Whereas CMB continued to cool down as 1 plus z. So the gas cooled down until the first heating sources appeared and started to heat up the gas. When this transition happens from cooling to heating, we don't know. It hasn't been probed, and we can only build theories to predict this redshift of this event. Then gas gradually was heated up by the sources until the temperature of the gas reached the temperature of the CMB, which also happened at unknown redshift, roughly around redshift 10 or 11, depending on the model. And eventually, the temperature of the gas was very hot. Also, the gas was ionized by UV photons and heated up by these photons, in addition to X-ray photons. So how this thermal history can be dressed upon this cartoonish version of the evolution of the history of the universe, in which you can see the ionized bubbles growing and merging. We don't know exactly. We don't know how cosmic milestones correspond of heating correspond to the ionization processes and so on. So I will show you some results of our work where we tried to test different scenarios of cosmic heating. So there are many unknowns when we talk about heating. In particular, we don't know the nature of heating sources, spectral energy distribution of these photons, efficiency of these sources, and also timing, as I just mentioned. And in literature, many candidates for X-ray sources are discussed, such as X-ray binaries, mini quasars, thermal emission from IGM and galaxies, dark matter annihilation, shock heating, magnetic fields, and many other sources. So here I will discuss 3 possible sources. One is the origin of soft X-rays, which can be fitted. The spectral energy distribution is just a power law. And the other 2 are hard X-ray sources, which are mini quasars and X-ray binaries, and they are most likely to be the dominant heating sources at high redshifts. So I will briefly describe which type of sources. So first, high mass X-ray binaries. As we heard yesterday from Jen Chaiki, primordial gas tends to fragment, and so we likely form several stars and several black holes, or several stars and black holes in one cloud. And we also know that population 3 stars are most likely massive, so there are high chances to get to obtain a high mass X-ray binary when we are talking about high redshift environments. As was recently shown by Fragos et al. In this paper, it doesn't work. X-ray luminosity of X-ray binaries win over AGN when we go to higher redshifts. In particular, he showed that for a population of X-ray binaries, the X-ray luminosity wins over AGN at redshift 6. So again, this shows that X-ray binaries are probably likely sources of heat at the high redshifts. And they were proposed to be to hit the IGM at high redshifts by Félix Mirabel, who is here. And he also discussed in the paper with Avi Loeb and Mark Dijkstra about the implications of these sources for 21 centimeter signal. So high mass X-ray binaries were shown to have a hard spectrum of this type. And as Fragos showed in this paper, the shape of the spectrum doesn't evolve with redshift strongly, but the normalization does. In particular, it increases as the metallicity drops. So at higher redshifts, we expect to have the sources more efficient than today. In his work, where he Fragos studied the evolution of population of the X-ray binaries with redshift, he found, in agreement with observations, that total luminosity scales a star formation rate with a scale with 3 times 10 to the 40 times some efficiency in units of arc per second per solar mass per year. So again, if we are talking about low redshift counterparts, they are less luminous than actually their high redshift X-ray binaries. Second type of sources, which I will discuss, are mini quasars. So at high redshifts, black holes were likely very different than we observe today. They were smaller, 10 to the around 100 or 10 to the 4 solar masses. And we use the internal feedback model proposed by Stewart and Avi in 2003 to relate halos to the mass of black holes to actually understand how much X-ray photons each black hole would emit. Then we assume Eddington luminosity for each mini black hole, lifetime of around 10 megayears, and we assume that each black hole shines for this lifetime, and the separation between black holes goes with the rate of mergers. So this gives us a measure of the luminosity which such a population could emit, and compared to the luminosity of X-ray binaries, it's something like that, a function which has a weight compared, which depends on the mass of the halo. So it's halo mass divided by 10 to the 8, which means that at very high redshifts, these mini black holes were not very not numerous, and the main contribution would come from X-ray binaries. But actually, at lower redshifts, when heavier halos form, they can be very important. So these black holes have very similar spectral energy distribution to X-ray binaries, which is hard, and in our model we just take the same spectral energy distribution but a different build-up history of this population. So just to summarize, we have hard spectrum for mini quasars and X-rays, and soft power law spectrum for other sources, just for comparison. The main difference between hard and soft X-ray sources is in the mean free path of X-ray photons that they emit. Hard sources can have mean free path of 100 of megaparsecs, and for soft sources it's much smaller. And as a result, hard photons would redshift a lot until they can get absorbed by the IGM. So part of the emitted energy gets redshifted away and lost to cosmic expansion. And therefore, effectively, hard sources are less efficient, and they input less energy into the IGM than soft X-ray sources with the same normalized luminosity. As a result, if we normalize the sources themselves equally, the thermal history in the case of soft sources is advanced compared to the case of hard X-ray sources. Heating happens earlier. And also fluctuations in gas temperature are stronger. So in the case of hard X-rays, they would be washed out because of the large mean free path of photons. All the scales that are smaller than mean free path are washed out. So we wouldn't observe fluctuations in gas temperature, and as a result in the 21 centimeter temperature. So in the remaining time, I will discuss imprints of both hard and soft X-ray sources in 21 centimeter signal Then I will normalize the efficiency using soft X-ray background, and we will see what does it imply for 21 centimeter signal, and I will also make some comments about the signature in the CMB. So again, heating error was an extended period from the moment when first sources appeared and started to be important until the gas temperature is very high, and effectively temperature fluctuations saturate and don't affect observables such as 21 centimeter signal. By observing 21 centimeter signal from this era, we would pin down the timing of cosmic events, which we don't know at the moment. We will understand how heating occurred and what was the efficiency and the nature of this high X-ray sources. So if luminosity function is not very predictive, 21 centimeter signal should tell us a lot of information. As we heard yesterday, today, and we'll hear tomorrow, there are plenty of experiments on the 21 centimeter signal planned and realized already. And we just heard from Josh Dillon about paper and hearer and MWA. We heard from Leon about Wolfer, and we will hear from Lincoln tomorrow about LIDA. So these experiments will be and are probing the 21 centimeter signal, and we'll be able to hopefully constrain efficiency and nature of high redshift sources. So to model a 21 centimeter signal, I use a semi-numerical or semi-analytical hybrid, whatever code, which has coarse resolution, and we use subgrid models to input sources. But we do have correct implementation of large scales. We have initial conditions for large velocity fields and density fluctuations, and we do have we propagate our photons with the correct power spectra, with the time delays and so on, and the optical depth. So it should be able to capture correctly the physics on large scales. And of course, on small scales, we calibrate our simulations to observations and to proper numerical simulations. So fluctuations and the global 21 centimeter signal depends on many physical processes, such as density and large-scale velocity modes, and various radiative backgrounds, such as X-rays, Lamn alpha, Lamn Warner, and ionizing backgrounds. And here you can see an example of how large-scale velocity fields affect the 21 centimeter signal. I'm not discussing it today, but you can please feel free to ask me about this. So the expected shape of the 21 centimeter power spectrum as a function of redshift at a given wave number has a series of peaks. One contributed by Lamn alpha photons just when the first stars formed and started to emit Lamn alpha. Then there is peak contributed by heating fluctuations and temperature, and this is mainly due to X-rays. And then UV photons imprint ionized gas and imprint ionizing fluctuations. So I'm interested to know how nature of X-ray sources affect this power spectrum and the global signal, which is schematically shown here. So first of all, how much time do I have? First of all, let's take a look on this dark blue curve. On the left-hand side, you see the case of soft X-rays, and on right-hand side, the case of hard X-rays. So you see that in the case of hard X-rays, we don't see the heating peak, which we clearly see in the case of soft X-rays. This is because the large mean free paths of the X-ray photons just wash out information on these scales. So by not observing the heating peak, we can pin down the mean free paths of X-ray photons, and thus the hardness of the spectrum. This affects predictions for ionization, because in some cases, if X-rays are hard and the efficiency is as predicted by Fragos et al., the temperature of the IGM is not much hotter than CMB during the most of the reionization, and this brings fluctuations to the lower. The fluctuations are much lower than in the case of the soft X-ray sources, which you see here with the dashed lines. all the solid lines show the predictions for the hard spectra with different normalizations. And the global signal looks very much different. So when we have hard X-rays, they're not so efficient in heating, and this trough is suppressed, is deeper because we have more time for the universe to cool down adiabatically. So this is how it looks like. On two up plots show the case of hard X-rays for temperature and brightness gas temperature and brightness temperature of 21 centimeter signal at redshift 12.1 when ionization fraction was 14%. And the two bottom plots show the case of soft X-rays. So we see that heating is much stronger and the fluctuations are much bigger, much more profound in the case of soft X-rays. So the signatures are completely different. I'll skip this. Then we can use unresolved X-ray background to actually normalize heating efficiency of this X-ray sources, and this gives us the upper limit on the heating efficiency. So it's interesting to know how much heating we can actually get using this normalization. So we know that about 12% of the soft band measured by Chandra of the X-ray background is still unresolved. And here in this work, we assume that this 12% go into pre-ionization sources. So it's contributed by pre-ionization sources. And we wanted to know the upper limit on FX. So the X-ray background contributed by the soft and hard spectra looks similar in the soft band of Chandra. But the hard X-ray sources are actually more efficient in producing this X-ray background because this Chandra band, if you redshift it from the epoch of ionization, captures nearly the peak of hard X-ray sources, whereas for soft X-ray sources, this band lies far away from the peak of the spectral energy distribution. So effects for hard X-ray sources will be much smaller, so we need less efficient X-ray sources to create the same X-ray background, whereas in the case of soft X-rays, we need strong heating sources. So just details. So for the case of mini quasars, we found effects of roughly 20, X-ray binaries roughly 15, and for soft X-ray sources, it was roughly 50. So this is the upper limits. And to see how it impacts the global signal, so the solid lines show the upper limit, and the dashed lines with fx equal 1, so the normalization to what Fragos found in his simulation. So we see that the worst case scenario is that this trough is only minus 37 millikelvin. I don't know if it's measurable, but probably it's on the verge of being measurable by future telescopes, but it's really the worst case scenario. And in our realistic predictions are these dashed lines, which are roughly minus 150 millikelvin and up to minus 250, which should be relatively easy to measure. So for the power spectrum, at 0.2 inverse megaparsec, we see a similar picture as I just showed for the fluctuations from ionization at low redshift. So in the case of strong X-rays fluctuation, it doesn't work. Fluctuations from ionization shown here, much stronger when we use the upper limit for heating efficiency, whereas in the case of fx equal 1, we can find that fluctuations are very much suppressed because, again, the gas is not hot enough during ionization. More interesting signature is at higher redshifts when the strong heating erases. In the case of hard X-rays, we don't see the fluctuations on the scales of 0.2 inverse megaparsec shown here. And for the Lam alpha peak, it's even more interesting because X-rays actually emit X-rays can generate lambda alpha, and they anti-correlated to the lambda alpha emitted directly by the stellar sources. So you see that in the case of soft X-rays, this lambda alpha peak is much smaller when heating efficiency is strong compared to the case when heating efficiency is just equal to 1. So there are more things here to discuss, and I will be happy to share it with you. Okay, I'll skip the rest and jump to conclusions. Sorry for being late. Thank you very much.
On the X-ray background imply, what we found is that it's quite sensitive to how long you let these sources live, right? If you turn them off at a certain point, and also what you assume is the very hard spectra. So there's a disconnect between what the X-ray background observes, which is 1 plus z times 1, right? So at redshift 15, you're probing 10 keV emission. And what is actually creating the heating. And so there's observational claims that there are needs when you get down to a few keV that break this kind of spectral slope. So I was wondering if you could comment on if you turn off the sources at some point, or if you kind of looked at various other spectral shapes that induce some kind of suppression or needs.
Well, of course, if you have a knee exactly at these frequencies, you will not be able to constrain.
It's not exactly at these frequencies, but it is. I mean, this is I forget the survey, but this is like they are finding these in galaxies that it's around 10 keV or a few keV. The slope flattens. Right. So here we use this population synthesis simulation predictions from Fragos, and he doesn't observe any. He doesn't show any. This is a model. It's not.
This is a model, but yeah.
But do you leave them on until redshift 0? That was the first part of the question.
No, we switch them off as soon as reionization ends. So this is just a prediction for pre-reionization heating sources.
So at 6 you switch
At 6 we switch them off.
Because it's very sensitive to
yes,
where you
I know
cut them.
Hi. In the past, people tried to understand the origin of the X-ray background by cross-correlating it with galaxies and other sources. And we heard earlier about cross-correlating X-ray background with the infrared background. So it seems to me that probably if one day you'll be able to cross-correlate the 21 centimeter data with the X-ray background directly, you will have a clean test of your hypothesis.
So indeed, people who are doing X-ray surveys in particular in Harvard, they're interested in developing this cross-correlation and understanding how can we constrain one signal with the other and how it works. It's a good idea, but we are thinking about it.
Yeah, I do have a question. So the mini quasar that you have at 10 to the 2, 10 to the 3 solar mass, where do they come from? So what are you thinking about their origin? So are they stellar black holes? What are they?
Yeah, stellar black holes.
With 100 solar masses? Or
yes, if you have if it collapses.
And so how do you set the abundance of these things?
The abundance, so we employed this model from Stuart White and Loeb. It's an internal feedback model, and then for every halo you can halo mass you can relate it to the black hole mass.
So there is one per halo of these things?
Yes, we assume that there is one per halo.
Okay. Felix?
Well, a few years ago it was reported from a balloon experiment of NASA, Arcade 2, which the existence of a background radio emission, cosmic background radio emission, that with NRAO, Condon and collaborators couldn't spot in any visible galaxy. So the hypothesis is that this X-ray, this radio background is coming from cosmic distances. Have you tried to simulate this using X-ray binaries? We know every X-ray binary produces radio emission.
Not yet,
but
I will be happy to discuss it with you.
Yes, because it will be interesting to see, besides the correlation between X-rays and infrared,
Right, indeed.
if this radio background will correspond, and perhaps you could identify the type of sources that are producing this.
Can it be measurable
Sorry?
Can it be measurable after redshifting from high source?
Well, this is measured actually at gigahertz frequencies. I mean, and you can postulate well what is the number of sources that will produce that, and see if these are X-ray binaries or not.
Let's discuss it during the
So much energy there that I doubt, but you should try. Okay, any other question? No, so let's thank Anastasia again.